We've seen that the Schrödinger equation can be rewritten in operator form, and that form would look something like this. But I want to go back to our discussion of operators to say something about what operators actually do. We know about functions, for example, that they basically convert one position into a new position. All right, so they're going to convert a number into a different number, okay, by simply plugging in the old number. Operators do this same sort of thing, but they do it with functions. So they're going to start with one function and convert it into a different function. So in general, if I have some operator A operating on a function f, the result of that operation is going to be some other function g. It's going to change that function. But what I've written here for the Schrödinger equation is something that is fundamentally different from that sort of picture. Because what have I done here? When I've taken this Hamiltonian operator and operated on this wave function psi, instead of giving me a new function back, it's given me the same function but multiplied by a number. Well, it turns out that this is a very special kind of equation. It's something we call an eigenvalue equation. And let's talk a little bit about what that means. All right, so the essence of an eigenvalue equation is when an operator returns the same function that it operated on. And obviously, it changes some because we've scaled it now by a new number. So there is, if I were to draw an analogy here, I might say, well, let's suppose I have some kind of operation on a vector, and I've got a vector that's sitting up here, and my operation sometimes will take that vector and turn it over here. Okay, so I've basically rotated the vector around, by some amount. I guess that's actually, I've rotated it by this amount. Okay, but it's changed that vector. That's the same sense in which operators can change functions from one function to another. So this eigenvalue equation is equivalent to saying if I started with some vector here, that the result of my operation would not be to create a new vector, but to simply change its length. It's pointing in the same direction, but it's now got a different length. So I've done that with functions now in this case when I've got an equation that looks something like this, where I've taken my operator on a function and I simply multiply it by some number. So this is just a number. All right, so let's define what some of these terms are. Okay, the A is our operator, and it's really at the center of these eigenvalue equations. It is the one thing that we know for certain in this eigenvalue equation to begin with. All right, so whenever we have a situation that looks like this, then we would call f an eigenfunction of this particular operator. Okay, it may not be an eigenfunction for a different operator. All right, other functions may not be eigenfunctions for A, but in this case, when this equation holds true, we know that f is an eigenfunction of A. What about this term here, this constant? A would be the eigenvalue that is associated with the eigenfunction f. All right, now again, if I operated on f with a different operator, say b, so let's say I did this, I may not get an eigenvalue equation. I may get that this is just equal to some different function. So I haven't regenerated an eigenvalue equation at all. So in other words, f has this special relationship with a, but it does not necessarily have that special relationship with other operators. And this eigenvalue a is associated with this eigenfunction. If I were to find a different eigenfunction of a, so let's say I operate this on a function h of x, and it also is an eigenfunction of a, I might get a very different eigenvalue associated. In fact, I normally will get a different eigenvalue associated with that function. There are cases in which more than one eigenfunction can give you the same eigenvalue, and we'll talk about that special case a little bit later. But our more common case is going to be where we have every eigenfunction has its own eigenvalue. Okay, and when it does not, this is a special case that we'll talk about in a little bit. All right, so this gives you a general feel for what these eigenvalue equations are about, but let me also indicate that I could take a sum of this function and this function that are both eigenfunctions of A, and if I operate on that sum, so let's say I have C1 f of x plus C2 h of x. A will operate on each of these individually. So I'll have C1, A operating on f of x gives me A times f of x. And A operating on h of x gives me B times h of x. Now notice that because A and B are not necessarily the same value, I'm not getting an eigenvalue equation from the operation of A on this sum of eigenfunctions. Okay, that will only happen if fortuitously they happen to correspond to the same eigenvalue. All right, so this is something that is a useful property to know about eigenfunctions and eigenvalues. You can't just take a sum of a pair of eigenfunctions and expect that result to also be an eigenfunction of a given operator. We're going to be seeing eigenfunction equations, eigenvalue equations a lot in this course because that is how we solve the Schrödinger. The Schrödinger equation is an eigenvalue equation, and the eigenfunctions of the Schrödinger equation are going to be the state functions that we care about when it comes to atoms and molecules. So we'll see a lot of examples of this. So this is just sort of an initial announcement that this is coming and we need to pay attention and learn a little bit about eigenvalue equations.